Good morning, everybody. Welcome here to the NASA's Wallops Flight Facility on the Eastern Shore here in Virginia. We are here for the NASA Social for the launch of the LADEE mission. I'm Jason Townsend, NASA's Deputy Social Media Manager, and today starts our two-day journey for the NASA Social to launch. Over the next 2 days, everybody here is going to learn more about this unique mission and see many of the unique facilities that are here at Wallops that enable NASA to study the Earth in incredible ways and enable us to access space by launching amazing missions like LADEE. But before we start going into too much detail, for the benefit of the viewers who are on NASA TV, just what is a NASA Social? Well, a NASA Social is all about taking the online, taking it offline. So we invite our followers, our fans, and our social media community members out to NASA facilities to go behind the scenes and see the unique things that we're doing here, to meet our passionate employees who work on missions and those from the NASA social media team, but also to share the experience back online through all of the NASA followers out there. If you aren't a space geek now, come on out to a NASA Social. We'll make sure you go home a space geek, that's for sure. You can find out more about these incredible opportunities and everything about them at nasa.gov/social. You can also follow us on Twitter at NASA Social. But back to today. To be really honest, we hope that you're going to follow along and join the conversation. If you're online on Twitter, make sure to follow us on @NASA and @NASA-LADEE. That's NASALADEE. On Twitter, or you can also find us on our NASA Facebook page and our Google Plus page. You can also use the hashtag for the NASA Social today, which is #NasaSocial. In today's televised event, we're going to be bringing you some of the behind-the-scenes information about the Lunar Atmosphere and Dust Environment Explorer satellite, better known as LADEE. We hope you learn a little bit more about this robotic probe that's going to be launching to the moon. It's bound to study the moon's atmosphere, the lunar conditions near the surface, and the environmental influences of lunar dust. Today you'll hear from a variety of different folks who each have a unique perspective on this mission. Everything from the hands-on science work to the big picture view of NASA's science programs and how this mission fits into that. Does anyone here know how many NASA social or tweet-up events we've hosted? Anyone? Well, this is number 71. This is the 71st in-person social media event of this sort for NASA. In the past 12 months alone, we've brought in over 1,200 social media followers to NASA events from coast to coast. It's experiences like these that really break down what we do here and really help us share NASA to new audiences in new ways. It really allows us to work to show off the science and engineering work that's going on here at NASA. We strive every day to promote the diversity of amazing work and to share our missions, our programs, and our absolutely talented employees in ways that really connect and resonate with everyone. The NASA Socials are just one part of this strategy, and this strategy is always evolving. We're always looking for new opportunities to connect with new audiences and share information in new ways. We're always exploring where you guys are going online, what you're looking at, and where we can find out where social media is headed. We're also on the most popular platforms out there, and new ones will emerge. In fact, tomorrow we're going to be officially announcing some new NASA presences, so stand by for that. In a way to get inspired and everything, please make sure to follow along online. Thank you for joining us for this event and this experience. No matter if you're offline here in person, in real life, #IRL, or watching online, we are glad that you're able to join us today for the incredible mission. This really is a mission of many firsts, including the first flight of the Minotaur 5 rocket, the first flight testing a high data rate laser communication system. Lasers. And also the first launch beyond Earth orbit from NASA's Wallops Flight Facility here. The LADEE mission is also the first spacecraft designed, developed, built, integrated, and tested by the NASA Ames Research Center in the heart of Silicon Valley. So without much further ado, I'd like to welcome to our NASA Social our very first speaker, Dr. John Grunsfeld. He's the Associate Administrator for the Science Mission Directorate at NASA headquarters in Washington, D.C. He's also an astronaut and a veteran of 5 space shuttle flights, and he's visited the Hubble Space Telescope 3 times during these missions. So now he oversees all of NASA's science programs. So without any further ado, welcome John.
Thank you, Jason. Well, it's really a pleasure to be here at Wallops Flight Facility for a lot of different reasons. And so I thought maybe I'd just tell you a little story of my life. So I hope you have a few minutes. But I grew up and spent a lot of time looking at the moon. So here for the LADEE mission is really exciting for me that, we're one day away from going to the moon. Well, it'll take a little while to get there, but that's okay. We're going to launch on our way to the moon with LADEE. But I grew up at a really amazing time, and looking out in the audience, there's a few people here who grew up in a similar time. And that's a time when humans had never been to the moon. And so I got to grow up with Mercury. I don't remember very much of Mercury, but the Gemini program, and of course Apollo. And I was in summer camp in 1969 when Neil Armstrong and Buzz Aldrin first set foot on the moon. And so I'm just thrilled that we're going back. And one of the things they did is when they landed with the lunar module, they kicked up a lot of dust. And there was a lot of discussion about what would happen when Neil stepped off the ladder. Would he sink into the dust, up to his waist? Would he be swimming? Would it, make any difference at all? And of course, in fact, if you look in the back of the room, there's the iconic Apollo footprint. So we know the moon is a dusty place. But what we didn't know is that the moon has an atmosphere, a very tenuous atmosphere, really an exosphere, so thin that atoms and molecules that leave the surface basically escape rather than colliding with each other the way they do here. So we're going to go investigate that. We're going to investigate dust that gets levitated by means that we don't fully understand, but we have some ideas, some theories, with ultraviolet light ionizing, perhaps electrostatic levitation at the terminator day-night. And so we're going to fly really close to the moon, as close as 12 miles, and investigate that. And then also look at what the atmosphere is made out of. Of course, we know what the Earth's atmosphere is made out of. We don't know what the moon's atmosphere is made out of. And we're going to learn about that. And the moon is also a reference point for Mercury, for other relatively dry moons of other planets, and maybe exoworlds, other worlds around other stars. And of course, we know about hundreds of those, and there are thousands nearby. So very, very exciting. So growing up, I got to see that whole moon mission. Well, I decided I wanted to be an astronaut at about age 6, watching these astronauts on Gemini and then later Apollo. But I love science. Clearly, I love science because I have the best job now for NASA's science programs, and we basically do Earth science, solar system science, astrophysics. So we rule the universe pretty much in terms of science. So it's an exciting job to have day by day. But I always wanted to leave the planet. And studied very hard in science and cut my teeth launching high-altitude balloons with science experiments under them. As an undergraduate, I had the opportunity to be involved with an experiment, X-ray astronomy, launching a balloon in Texas. And then as a graduate student from all over the world, I launched high-altitude balloons with experiments on them. And I just loved going out into the field, preparing an experiment, getting it ready for the launch pad, and then that critical moment when the truck holding the balloon payload, it's a space vehicle, goes to the edge of space, let go, and off it would go, and all of my hopes and dreams of getting science back, would go up with it. And it was dependent on me to have that payload ready. So I know the LADEE team is really excited for tomorrow. They have their payload ready to launch, and they'll be excited about 1,400 seconds after launch when it's powered on and we get the first telemetry. So that's their day tomorrow. But I launched these high-altitude balloons, and in fact, that program of high-altitude balloons and rockets, suborbital rockets, is run out of the Wallops Flight Center here where you are. So I hope you enjoy some tours looking at that, but this is the center of it all, although the balloons are launched all around the world. We have a team in Fort Sumner, New Mexico right now, launching or preparing to launch high-altitude balloons with a variety of science experiments, earth science, heliophysics, astrophysics, and student experiments. We just launched successfully 9 student experiments. So I love scientific ballooning. I love space. We're heading to the moon. It doesn't get much better than that. And I think at this point I'm open to taking questions.
You guys have a question? Raise your hand. Okay, get ready for the Q&A. Oh, don't be shy now. Okay, this is an astronaut here. You guys have got to have a question.
Okay. You guys have a studio.
5 missions. Do you have a favorite?
Okay, so the question was 5 space shuttle missions. Do I have a favorite? And actually, that's a tough one because the first space mission is always special. I went up on Space Shuttle Endeavour for 16 days, and in the payload bay were 3 astronomical telescopes, ultraviolet telescopes. We have an ultraviolet telescope on LADEE, an ultraviolet spectrometer, and it was 1995. And for me, it was amazing because I went from being a senior research fellow at Caltech, going to mountaintops to observe space, and just 3 years later, I was in space being the telescope operator for some ultraviolet telescopes and spending 16 days in space. And of course, it's really great operating a telescope, doing long integrations, up to 40 minutes of integrations on one. For instance, looking at the moon Io of Jupiter and watching a sulfur volcano erupt on a moon of Jupiter from low Earth orbit. That's pretty cool. Plus, the telescope is doing this long time exposure, and that gave me some time to look at the Earth too. So astronomy missions are pretty good, and looking at the Earth is just amazing from space. That's, for almost every astronaut, the most favorite thing to do. So the first mission is very special, but I have to say my favorite mission was this last one. May of 2009, we went up to the Hubble Space Telescope and really did not quite a complete makeover, but a pretty substantial makeover of the telescope, repairing 2 instruments that were broken, installing a new ultraviolet spectrometer, the Cosmic Origin Spectrograph, repairing some power system components, computers, putting in new batteries, a new fine guidance sensor, which is an interferometer that allows Hubble to point so steady. And Hubble is still doing great. So we didn't break the telescope, we fixed it, and everything's going great. So I think that mission, commanded by Scott Altman, a close friend and a great commander, we did everything we set out to do and a little bit more, and left Hubble in great shape for the future. So that was a fun mission. Hard, but fun.
Since you're an astronaut, I want to ask you an astronaut question. Being in the space shuttle, and it's pretty roomy. I haven't been inside, or just from photographs I've seen, but I've seen a couple up close. What do you think of the room that the new astronauts in the SLS, or how are they going to cope compared to the room you had in the space shuttle? Do you think it would be more cramped and tougher to work together?
So the question really was, the space shuttle is pretty roomy. How does that compare to what the Orion spacecraft will have? And it's not quite a fair question. I mean, every question is a fair question, but it's not a fair comparison. And that's because the space shuttle was designed to be a rocket to get you to space, which we then converted to our house in space and our laboratory in space, and then to be, a kind of high-speed glider entering back into the Earth's atmosphere. And so it was designed to be very versatile and to do all these different things, to have places to sleep, to eat, to put spacesuits, airlocks to go out and do spacewalks, and of course a payload bay where you could put modules even. And so on my second flight, we had a Space Hab module, which we did science research, and we carried supplies up to the Mir spacecraft and back. So it was just designed that way, and it's really nice to have all that room. On the other hand, when you consider in Columbia on the last mission, we had 7 people, 4 spacesuits. We had enough gear and supplies to repair the shuttle if something happened externally to tiles or carbon on the wings, and we had 25 days of supplies in case we were stranded in space and all kinds of other things. It was pretty cramped, actually, because the 4 spacesuits, that's like having 4 really big guys inside as well as the 7 of us, so it was like having 11 people on board. But the Orion really is designed to be not the place that you live, but the spacecraft that takes you to somewhere where you would have a deep space hab, and you would go to someplace far away, say an asteroid, moon, Mars, down the road. So it's our exploration transport vehicle, not really our exploration hab vehicle. Now we do have a very ambitious mission that we're looking at mission planning for now, to go out to a translunar space, a very interesting lunar orbit where we'll rendezvous with a captured asteroid. And for that mission, we're looking at 2 crew members, and actually at 5.5 meters diameter, the Orion spacecraft will seem quite roomy.
And that's your first mission.
And that's the first mission, queued up for next decade.
That's a pretty brave undertaking for a first mission.
Now, if you want to know about cramped, think about Frank Borman and Jim Lovell in a Gemini capsule, which is like riding in a 2-seater sports car for 14 days. That's cramped.
Hi. How do you keep your concentration when you're doing a complex EVA like in the Hubble, when the Earth is going by and all you want to do is look out? And also, how does it feel to be on the dark side when the sun goes down? The same EVA.
Is that a dark side of the moon question?
No.
Dark side of the Earth. So the concentration question is a good one. And I just enjoy activities. When I was a little bit younger, I spent a lot of time rock climbing. And one of the reasons I like rock climbing is it's a hazardous activity. You have to pay attention, and it requires an extraordinary degree of focus because you don't want to fall. And I find that very relaxing in a way, not stressful, that you can focus on that task and to the exclusion of everything else. I would hope if I ever need surgery that the surgeon has that same kind of focus, that he's not worrying about, oh, if I nick something, the patient will die, or, I'm going to go play golf later, or anything else other than, that specific task. And I think it's part of the way the human brain works in very technical activities. Flying is another example. When I'm flying, I'm flying the airplane, I'm thinking about that. I'm not thinking about, sports or family or other things. I'm just concentrating on, navigating the airplane and flying the airplane, especially in critical phases of flight, takeoff, landing, a lot going on. And I get a lot of enjoyment about that kind of focus. And maybe that's why I was successful in science and then as an astronaut. And so during the spacewalks, focusing on the task, communicating with the folks inside and my crewmates, nothing else is going on in my brain. It's no other subroutines in particular. There are some little safety subroutines going on, sharp edges, ooh, avoid that kind of thing. But really focus on the task. So much so that I really don't have very much recollection of sightseeing during the spacewalks. In fact, at one point, Drew, who was waiting for me to hand a tool, Drew Feustel, my spacewalking partner on the last mission, looked out and said, "Oh, look, Hawaii," and I was like, "Oh yeah, we're in space, we're orbiting the Earth." I was inside the telescope at the time, so I thought, "And thanks a lot, I can't see the Earth." But actually, I think he said something like, "Wow, that's amazing," and I said, "What?" And he said, "Hawaii," and I thought, But it's actually good, and I recommended on the last mission, I was sort of the Hubble lead, that the other spacewalkers look at their timeline and identify before we launched what little 2 or 3 minute or 5 minute segment is available when I'm not working or when they're not working, where you could plan to look around. Because my first spacewalk was 8 hours and 40 minutes. And I don't ever remember anything but the spacewalking tasks. We were so focused, we were so busy, things were going wrong, we were fixing things. And I just don't remember, looking around and saying, wow, we're orbiting the Earth, we're in a space shuttle, we're in a spaceship. Look how black the space is, nothing. And that's a mistake. We're still humans, we go up there, it's incredible. You're in a cloth spacesuit in a vacuum, that's crazy. And it's important to feel that and look around.
Hi, Dr. Grunsfeld. Just first of all, I just want to say thank you very much for all the work you did on the Hubble Space Telescope. I had the privilege of working on HST for several years at the Space Telescope Science Institute in Baltimore, and thank you so much for you and you and the crew and everybody who worked so hard to put those missions together. What was it like? My question for your service: what was it like to know that you were the last human being to make physical contact with the Hubble Space Telescope?
Well, we talked about that a lot with the crew and folks at the Goddard Space Flight Center that managed the Hubble project and others. And I pointed out that the last time I sort of let go of Hubble, actually the last contact was a little pat and a salute and a good luck, Mr. Hubble, the telescope. But I was wearing rubber gloves. So it's a really curious question. Who is the last human being to touch Hubble without rubber gloves? And that would have been, sometime in 1990 probably, although almost everybody who touched the telescope back then had, gloves on for contamination purposes. So we don't really know who the last person to touch, skin to metal or skin to paint or skin to aluminized mylar, the Hubble Space Telescope. What I find so incredible about the Hubble Space Telescope is that literally tens of thousands of people touched Hubble. All the people that it took to build the telescope, to create the optics, to create the instruments over 23 years. We're coming up next April, 24th birthday of Hubble. And then there's the literally, hundreds of millions of people, if not more, who have been touched by Hubble. Just an incredible human achievement. And it's the story of the Hubble Space Telescope, but it's a science story. It's unraveling the mysteries of the universe. It's telling us about our own solar system and the very beginnings of, creation itself and the beginning of the chemical elements and the evolution of stars and galaxies and planets. Nobody imagined that Hubble would be studying the atmosphere of planets around nearby stars and our own moon. We've done Hubble observations of the moon. And so just incredible the number of science topics and the number of people that Hubble has reached in science and the number of people that Hubble has inspired. For me, I was worried that, when we let go of Hubble with the robotic arm and it was drifting off into the distance, that I'd be incredibly sad. And in the moment, I wasn't. I was thrilled because we'd achieved everything we'd hoped to in repairing 2 instruments that lots of people said we would not be successful, we shouldn't even try because it was too hard. This was, the hundreds of tiny screws and pulling out circuit cards and things that nobody had ever done before in space. And everything worked. And so Hubble is fully operational now. And so I just felt very proud of our country, and the science teams and the instrument teams and all the engineers who developed those techniques and simple things, building a tiny little screwdriver that I could use in a big space glove. That all of that actually, in the end, worked. I was sort of amazed that it all worked, but there we were. So, I wished Hubble well, and it's doing well. So I still have no sadness that, we won't go back to Hubble again.
We've got time for one last question.
Hello. It's a pleasure meeting you. And I have a question about the space shuttle itself. When you're inside the space shuttle and the engines fire up the boosters and all that, you lift off the pad, can you describe what the physical sensations are like when the shuttle takes off? I mean, I know there's like acceleration, but I heard there's like sounds and other things. I think Story Musgrave had a particular name he talked about that the moment the engines kick on and the shuttle starts to shake and prepare to lift off the pad. Can you tell us a little more about that?
So the most interesting time is when you've flown multiple times, is the first launch. It's like shooting a pistol, if any of you have ever shot a pistol. The first time you pull the trigger, you don't know what to expect. And so, you're calm and relaxed, and, you can aim and all that. The second time, you know that there's going to be recoil, and you prepare for the recoil. But I digress. So the first time, the most amazing thing is, first of all, I was out on the launch pad, and unlike what we're going to see tomorrow night, when we walked out to the launch pad, it was raining, it was dark, stormy, and we were all convinced on the crew that we were not going to go launch that day, that it was sort of a practice event. And the countdown kept ticking down. It had been raining, so the front windows of the shuttle were caked with a little bit of salt rain that had dried on the screen, so we couldn't really see the big xenon lights, so we couldn't see whether there were clouds or not, too much scattering. And we got down to the 9-minute hold and held, and then came out of the 9-minute hold, and I thought, well, we have other built-in holds. We'll get down to just before we turn the auxiliary power units on, which are run by hydrazine, and they'll hold us there for an hour or so, and then they'll shut it down because that's our window. We'll get out, go back, call our families and that kind of thing, get some rest, get some exercise. And we got to the 5 minutes, and they said, go for APU start. And we turned the APUs on, and then I thought, great, we'll be out sooner, because you can only run those for a few minutes and shut them down and still be able to restart them for another launch attempt. And then they said, Endeavor, close and lock your visors. And suddenly, we all got really quiet. It's like, wow, we're going. Turns out a big hole had opened up in the clouds that we couldn't see, and there was no discussion about recycling or anything, and off we went. So there was really no time to get nervous or anything, but when we were in the last minute or so, I was sort of surprised I didn't have butterflies and that I was scared or anything like that. It was just, okay, we've trained for this, we know what to do, we're going to go. 6 or so seconds before launch, the main engine started, and the vehicle really came alive. I mean, there were just enormous numbers of vibrations. You could feel resonances and waves traveling up and down the vehicle. Endeavor's a lighter vehicle than any other space shuttles and more flexible. You could really feel what's called the twang. You could feel that because the crew, and we're up in the cabin, which is far away from the hold down posts, and so you really feel the vehicle going. And as it came back to vertical, sure enough, the solid rockets lit off, and then it felt like a train wreck. I mean, it felt like you're in a car and somebody hit you hard from behind in a big truck, because the shuttle really leaps off the pad. Incredible amounts of vibration. Hard to say about noise. We're wearing helmets. It did get very noisy, but we have the Snoopy caps on with the ear cups, a lot of noise isolation. But you could definitely feel it in your body. And through first stage, you could hear the air sound going up through the atmosphere till about 60,000 feet, and it was sort of the rushing of air, the whine, kind of a whine, increasing in frequency, a combination of the velocity as you go through the atmosphere and the density of the atmosphere decreasing. A lot of strange kind of oscillations as we went through maximum dynamic pressure as we were going through the speed of sound. And then all of that kind of started down in volume and vibrations as we got up higher in the atmosphere. Then a little bit of a pause, solid rocket motors come off, and then it got very smooth for the ride to orbit. And then the best part, main engine cut off, and suddenly, just like turning on or off a light, we're floating. And just a great feeling. So, but we're here to talk about LADEE. And so let me just close with, when I wanted to become an astronaut, it was to go to the moon, because that was the big thing. I had dreams about, exploring the moon and, doing the hopping. And I just imagined that by the time I was an adult, we'd have space stations, a la Arthur C. Clarke 2001: A Space Odyssey, that we would have encampments on the moon, and that we'd be going on to Mars. And it's just thrilling today to be able to be on the cusp of having LADEE going to the moon. We had the Grail mission, which was very successful. We have the Lunar Reconnaissance Orbiter around the moon. We're learning an enormous amount of our partner here around the Earth. We have Curiosity and Opportunity and Mars Reconnaissance Orbiter on Mars. So even though I didn't get to go to the moon or to Mars, I know that young people today can aspire to that, because we will be going back, and we are going to be exploring Mars. We're just about to release an announcement of opportunity for instruments for a 2020 rover that will be like Curiosity, but the next generation of Mars exploration. So we have a lot of stuff going on. MAVEN in November, we're going to launch MAVEN to Mars. So in effect, we are all going to the moon with LADEE. We are all going to Mars. And I just want to remind everyone that LADEE, Curiosity on Mars, they're robots. They don't discover things. People do. And I encourage you to talk to the science teams. I know we're going to have some NASA socials with other scientists here. And it's exciting. Find out what they expect to get out of LADEE, and then hang on to the mission. And find out what LADEE really discovers from the science team members. So thanks very much. Jason, back to you.
Thank you very much. For folks who don't know, John is on Twitter. You can find him at SciAstro, SciAstro. And so you're welcome to follow him there and everything. So as he alluded to, though, there's some pretty awesome people behind this mission, and we're getting ready to hear from one of them. She is the program scientist for this mission, and her name is Sarah Noble, and she works at NASA headquarters on this mission, and will tell you a little bit about all of the neat things that they're either hoping to find, expecting to find, or maybe the unknown unknowns out there. So here we go.
Thanks, Jason. Morning, guys. How are we all doing today? Is everybody excited to be here? I can tell you that I'm really excited to be here. This is actually my first mission. We talk about LADEE as this mission of firsts, and I would like to add to that, this is my first mission. I've been studying the moon for a really long time, but now is actually an opportunity to get to go there, sort of virtually, but still. So I'm sort of equal parts excited and terrified at this point, but excited, sort of winning out. I was asked to talk to you guys a little bit today about the science that LADEE is going to do while we're up there. As you might have guessed from the name of the mission, the Lunar Atmosphere and Dust Environment Explorer, we have two science goals. We're going to study the lunar atmosphere and then also the dust environment around the moon. I want to talk to you a little bit about the lunar atmosphere, because I think sometimes people get a little confused when we start talking about a lunar atmosphere, because did you all not learn in school that the moon doesn't have an atmosphere, right? Yes. It does have an atmosphere. It's really, really, really thin. It's something like 10 trillion times thinner than the Earth's atmosphere. It's so thin that the molecules that make up the atmosphere are so few and far between that they don't interact with each other. They never collide. Like in our atmosphere, they're constantly colliding. That's what gives us air pressure. On the moon, they never collide. This is something we call an exosphere. There's a technical term for it, exosphere. And the Earth actually does have an exosphere too, but in fact you have to get up past where the space station orbits before you get to this environment where it's so thin that the molecules don't collide, and you can call it an exosphere. But on the moon, that actually happens right down at the surface. So we call that, here's the technical term, a surface boundary exosphere. Right. We like to name things in science, right? So this is what we call it, a surface boundary exosphere, or we like to use acronyms, an SBE. Right? And it turns out that SBEs, surface boundary exospheres, are actually the most common type of atmosphere we have in our solar system. It's not just the moon, but also Mercury. We've been studying that with the MESSENGER mission for a while now. A lot of the moons of other planets, a lot of the moons of Jupiter and Saturn and some of the other outer moons out there. Even some of our larger asteroids and Kuiper Belt objects actually are big enough to have what we call a surface boundary exosphere. So one of the cool things about LADEE is that we're not only going to learn about the moon when we go there, but we're going to actually learn about this whole class of atmosphere, which is something we don't know a lot about right now. And so it's sort of a great opportunity to go to some place that's nearby and easy to get to, and we can learn about the entire solar system from just studying in our local neighborhood. The other thing that we're going to look at is the dust environment, and we've been really curious about the dust environment around the moon for quite a while. It's even before Apollo, we had these weird hints from some of the surveyor landers that saw this strange glow on the horizon, and we don't know what's causing it. The atmosphere should be too thin to be scattering light in such a way that would make that glow, so we think it might be dust. Right? So now is finally our opportunity to go and see this and see it and confirm whether or not that's dust. The Apollo astronauts sort of saw the same horizon glow as well. And so we think that, again, that they maybe saw something that was, dust on the horizon. We're not sure. It seems like there's some sort of way to get dust lofted up into the atmosphere, and it's finally our opportunity to go and prove them right or wrong. So we're really excited about that. I just left the science team. They're meeting this morning. This is their last chance before the mission heads up to get together and make sure that they've got everything ready. This is a short mission. LADEE is only 100 days of science. So we get to the moon. It takes us about a month to get to the moon. We have about a month to check out our instruments and whatnot, and then we have 100 days to do science, which is really short. And so we have to be ready to hit the ground running. So they are off right now making sure that they are ready to hit the ground running and get every ounce of science out of this mission that they can. And they're really excited too. So it's going to be a really great mission. We are all really looking forward to getting her off the ground and on her way to the moon, where she can do some really cool things. I don't want to talk too long. Can we take questions? Okay. Yes.
Hey, thanks. I'm actually posing a question from the Reddit r/space subreddit. They were wanting to know, as far as the communications testing on LADEE, if the 622 megabit data link, if the data link goes well, what are NASA's plans of using that technology for HD streaming of video feeds from deep space, as far as in orbit or from Mars or even those asteroids that you spoke of? That was actually by user JJR. So thanks to JJR for
Fantastic.
Wanting to know what's up.
Okay, so the laser communication, which I didn't talk about, it's actually not one of the science instruments, but there's a demonstration on LADEE that is testing out whether we can use lasers rather than radio signals to communicate back and forth. And 622 megabits per second, whatever, is about 6 times what we can get right now. So we can get much faster data rates, which is awesome. We all want more data. Scientists, we believe me, we will take every megabit you can get us, right? So we're really looking forward to working on that technology. We're not really using it on LADEE for our data. It's just a test here. So we're going to use it test it out here, and so that at future missions we might be able to put it on spacecraft, and which leading to things like HD level quality. Again, more data is better data. So we are looking forward to developing this technology, but we're not using it so much on LADEE. So. Are there development plans already in There is this is again not my area, but there is. Thank you. It's okay. I'm doing my best here.
Hi, Sarah. What can studying the moon's atmosphere tell us about our own atmosphere, and what we can gain from that?
So the moon's atmosphere is pretty different from our atmosphere. As I said, we're something like 10 trillion times thicker. And the sources of things in our atmosphere are quite different than where we get sources from the moon. The moon's atmosphere comes largely from interaction with particles from the sun, sputtering different elements off into the atmosphere, as well as outgassing, argon that is created radioactively under the surface and sort of makes its way out. So the processes are pretty different. As I said, that the Earth does have an exosphere, and so sort of understanding some of the physics of how things interact in an exosphere, we might be able to learn. But the bigger key point is that atmospheres are really, really complicated, and we don't actually understand how any of them work very well. So these kinds of atmospheres, these exospheres, surface boundary exospheres, are sort of the simplest class of atmosphere. So by learning how these atmospheres work better, we can sort of start to apply that to more and more complicated systems.
I have a question about how will the science operations between LADEE and other lunar missions right now overlap one another? Will there be any complement or science to be gleaned from both simultaneously?
That's a great question. We are actually talking to the other teams. So I don't know if you guys are probably aware of these things, but maybe the general public is not, that there are actually 3 other spacecraft orbiting the moon right now. So there's the Lunar Reconnaissance Orbiter that's been up there for a number of years, doing a great job. And we've been talking with that team quite a bit about ways that we might interact with each other and build off of each other. There's also 2 tiny little spacecraft called Artemis. Has anybody here ever heard of Artemis? Oh, good. Look at you guys. You are on top of these things. Yes, so Artemis is a continuation of a mission that was studying the sun called Themis. Themis had 5 little tiny spacecraft that were studying how the sun interacts with the Earth. And as that mission finished, they moved 2 of those spacecraft around the moon to understand how the moon interacts with the sun, which is great for us because the sun is one of the big inputs into both this dust atmosphere and the solar wind. And so Artemis is going to be able to sort of give us space weather reports and tell us how the sun is doing as we go through the mission, how active is it, and what's going on with the sun. And that will help us understand how the sun is interacting with the lunar atmosphere. So we're actually talking a lot. We've got some coordination between the teams to make sure that we can maximize the science for both missions.
Time for 2 more questions.
In 2009, the LCROSS mission found water on the south pole of the moon, and there was a lot of discussion at that time and immediately thereafter talking about water cycles on the moon. Is there any investigations that LADEE is going to do with any of its instruments that it's looking at how that kind of material migrates around the moon?
Absolutely. That's one of the big goals of the mission is to try to understand the water cycle on the moon. So the solar wind implants hydrogen, has a lot of hydrogen in it, which hits the surface and interacts with the material on the ground. We think it's creating hydroxyls, HO molecules, that bounce around. They don't stick very well. They sort of bounce around, and we think they eventually bounce to the poles and get stuck there. That's what LCROSS was seeing in the poles. And so we'll actually be able to see the sort of bouncing around near the equator. We are in an equatorial orbit, so we don't go over the pole, but we can see what's bouncing around as we fly around the equator. And so that will give us a lot of clues into how this hopping that we think is going on actually happens. Yeah. Oh, sorry.
Hi. The couple of the LSEP experiments looked at lunar dust and atmosphere. Will those data sets be usable to give us like a timeline of what's happened over the years?
The LSEP packages.
Yeah.
We do have, yes, that data is around. We have been comparing it. So there was a couple of experiments on Apollo that looked at atmosphere. There was one called LEAM, the Lunar Atmosphere, Lunar Ejecta. It was looking at micrometeorite impacts onto the surface. And actually what they found was actually these weird spikes at sunset and sunrise, rather than the sort of steady stream of micrometeorites. And what they think they actually saw was the dust moving around. it sort of seems to peak right when you turn from light to dark and dark to light because of the mechanics of the way that the moon interacts with the sun. So it charges positively on its front side, on its day side, and negatively on its night side. And so right when you cross the terminator, when you go from day to night, there's a charge imbalance. And so we think that it causes dust to loft up as it's trying to balance itself charge-wise. Another experiment was looking at the atmosphere. It's called LACE, I believe. Was looking at the atmospheric components. And it's interesting because they've found LRO has also been looking sort of at the atmosphere in various ways. That it can't do it as directly as LADEE is designed to, but they have found really some innovative ways to look at the atmosphere, and they've actually seen some different results than we saw on Apollo. And so there's some interesting, we're debating about whether that's because of the difference in looking at from the ground versus the air, or whether that's something that has stopped happening since the Apollo days, or there was something weird going on during Apollo. So there's all sorts of interesting questions we have that we want to compare what was going on in Apollo to what we're seeing today. So we are very excited to actually be able to compare the two.
That's all the time we have right now with Sarah, but we'll have more time with her later. Thank you guys very much. Thank you, Sarah. So you've heard a little bit about the science of the mission. Now we're going to talk a little bit about the actual spacecraft itself. I'd like to welcome Bob Barber. He comes from NASA's Ames Research Center, and he's the spacecraft systems engineer for this program.
Thank you, Jason. Good morning, everyone. It's great to be here today. It was really great to hear your introductions during the social, and I think your passion for this mission and for NASA is shared by the LADEE team, and we're great to have you here today. I'm going to talk a little bit about the spacecraft today. One of the things I want to go over is I'll be pointing to this model a lot to go over the spacecraft. Some of the key items and basic items for a spacecraft is it's 7.7 feet tall and about 5.2 feet wide. Essentially, it's very close to these two posters up here and similar in height and width. And that it weighs 835 pounds. That includes 297 pounds of fuel. So that's about more than a third of the mass is the fuel. And thinking about or relating that to your car, typically a car's gas tank is only about 3 or 4% of the mass of the car. So we carry a lot of fuel to get to the moon. It's a long drive. So we'll get in. The other aspect that I want to, as an overview, is that we are launching powered off. We're doing this primarily to reduce safety concerns and then also to reduce complexity of the mission when we design this. Going over the heart of the spacecraft is really the structure. This is the main body here. This structure is a carbon composite structure that is an innovative design that was performed by Ames Research Center. What this is it's a modular concept where there's, if you see here, there's 4 modules. It's a bus module. There's the payload module, the extension module, and the propulsion module down here. This is all these modules are formed by a single mold, and the innovative aspect of this compared to most satellites, most spacecraft, they build one structure that houses everything. Because this is a modular structure, for future missions, you can combine these in different fashions to make taller or shorter spacecraft. You could also potentially add legs to this and make a lander out of this. So this is one of the important innovative aspects of the LADEE mission. The other aspect of this main body here is you see all these blue items on here. Each of those is a solar panel. We have 30 solar panels. There may have also a carbon composite. The majority of all of our structure is carbon composite. On that, you have all the solar cells. We have over 1,800 solar cells on the spacecraft. It generates a little bit more than 300 watts of power for that. Also located around here, we have what's called Coarse Sun Sensors, and the Coarse Sun Sensors are used primarily to support our safe mode operations. They look for the sun, find the sun, and let the spacecraft know where the sun is so it knows where it is in our safe mode configuration. I'll go over some of the basic components on this, starting kind of at the top. Up here is the radiator assembly, which is aluminum face sheets over aluminum honeycomb. That's utilized to hold most of the avionics for the spacecraft. There's a top side, and then there's also components within the spacecraft. On the top side here, these two big black cones that you see, those are star tracker camera units. And what those look for is a star field for navigation and control of the spacecraft. So those are critical elements that we need to let the spacecraft know where it is relative to the star field. We also have, over on this side over here, for some might be difficult to see, we have an omnidirectional antenna. And we also have another omnidirectional antenna down here. Those are our primary communication antennas for the spacecraft, for commanding the spacecraft and retrieving data from the spacecraft. Another antenna we have right here is called the medium gain antenna. That's a high data rate antenna, not near as high as the laser comm, but that's our high data rate antenna to get our primary science data down that Sarah was discussing earlier. Additionally, on the very back side, we have what's called a sepia box. I mentioned that we are launching off. Since we're launching off, we need to detect when we separate from the Minotaur 5. The sepia detects when we launch off and puts power on the bus, which allows the spacecraft to boot itself up. And that's how we activate the spacecraft after separation from Minotaur. There's two science instruments on the radiator. One is the ultraviolet visible spectrometer, which helps gather science data. And then on the other side is a lunar dust experiment. And those are a couple of the key experiments to support the primary mission. The other key science instrument for primary mission is the neutral mass spectrometer on one side, and then we have the laser comm that we discussed as a communications and science demo. On the underside of this radiator panel, which you can't see, although one thing to note is these solar panels I mentioned, they are all removable, which allow us access to the internal components. So if during testing we have any problems, we can remove solar panels and get access to the components and swap things out. But under that side, we have several avionics boxes. We have a battery for storing energy that comes from the solar panels. We also have an integrated avionics unit, which is the primary kind of the heart and soul of the brain of the spacecraft from a data system perspective. The IAU that we call the integrated avionics unit also provides control of all the power distribution on the spacecraft. The S-band transponder that ties to these antennas is also mounted on the other side. And then we also have an inertial measurement unit, which is used to support the guidance and navigation system, is mounted there. Within this bus module, kind of at this level, we have inside our 4 reaction wheel assemblies. Those are our primary attitude control devices that we use for managing the spacecraft during its normal flight operations. For the burns that we do, we'll talk about the propulsion system here in a minute. So that's kind of the core of kind of the bus that takes the science instruments to the moon. Moving down to the bottom half is we have our propulsion system. Propulsion system is essentially all of the components down here. Inside the structure, we have helium pressure tanks, we have fuel tanks, and we have the oxidizer tanks. LADEE uses what we call bipropellant, which we use monomethyl hydrazine combined with an oxidizer, which is called mixed oxides of nitrogen. So you can Google those and look those up and learn about biprop systems. They provide a good impulse power for us to get to the moon. Those propellants are then fed through, we have small thrusters, 2 on each side, and then we have a big main thruster down here. Those thrusters are required to get us to the moon. We use the big thruster to do some loops to get us out of Earth orbit, and then to do our braking burn when we get to the moon to slow us down so we can get captured in the low gravity of the moon. And kind of the data and power that ties all of these systems together is comprised of over 1 mile of wires. So there's a lot of wiring inside this spacecraft, all spacecraft. There ends up being an extreme amount of wiring in there with a lot of connectors. So that gets very complicated, and that's why we go through a very intense integration and test process to make sure that we work all those out and verify all the data interfaces. And I think that's all I have for the spacecraft, and I'm ready for questions.
Hi, good morning.
Good morning.
So I had two questions. The first question was, since this is a modular type of structure, what other kind of missions have used this panel architecture? And then the other question was, what is the system design process that you go through? So how do you decide whether or not you want chemical versus electric propulsion? How do you decide what kind of communications, things like that?
Okay. So the basic questions were, I'm sorry, can you repeat the first question? Other spacecraft that use this module. Right now, none. This is a LADEE first, and a first for Ames. This was designed at Ames Research Center for the intent of future missions, being able to support future missions and know what NASA would term an assembly line kind of configuration. Not assembly line like the automobile industry or the high-tech industry, because they build millions or hundreds of thousands. But just us building a few or several is you could build multiple modules like this, and in that modular nature, be able to stack these modules and assemble them more quickly and build different configurations for spacecraft. So right now, LADEE is the first to use this modular concept. There's a prototype that was built before, but this is the first spacecraft that's going to fly. On the design process, the basic one is there's a process that's outlined where we do concept reviews, preliminary design reviews, critical design reviews. But the key items that feed into that are the trade studies, the items that you talked about, where the engineering team sits down and identifies what solutions there are to what we need to achieve and how to get to those most effectively, efficient, but it needs to be cost effective and schedule dependent. So you have to take in all the different parameters, the technical, the programmatic, and the cost, and generate those. You come up with trade studies, evaluate those, and determine which are the best solutions for what you need for your mission.
Hi, my name is Ulysses. Could you explain how the dust collector works?
Well, I'll try to explain a little bit. Sarah would probably be better at that. I don't know if I don't think they'll be coming in later, the dust collector guys. But what we typically do, the dust collector and the neutral mass spectrometer are in the direction of travel going around the moon. So their apertures for collecting the information or collecting the particles that come in are in the velocity vector or the direction of travel to enhance them being able to collect that information. And then internally, they'll process those particles based on specific designs within each one of those and determine, I think the dust collector, and Sarah might be able to correct me if I'm wrong, looks for different size particles and based on those particle sizes then tries to determine what the potential volume is in the exosphere. And Sarah's shaking her head yes, so.
I was wondering, it was like a vacuum cleaner, how it will collect the samples.
Yeah, it doesn't, it's really using the force that's coming, the opposing forces for us flying through the exosphere.
Hello. One of my 8th grade students was curious about how long it took to construct.
To construct. From assembly phase till now, I have to think back when we started assembling, probably a couple years to construct and test. The entire phase, of course, took longer from preliminary design, critical design. I'm trying dates, things have gone by so fast lately, I think lost on dates, but typically it takes a couple years to construct, and that includes, we usually allocate somewhere between a year and a half for integration and test, and that all depends on the complexity of the system. The goal is to make things simple for this type mission, try to simplify versus like Hubble, which was described earlier, or James Webb Telescope, which will take a much longer time frame.
Hi, can you give us an idea of the different disciplines of science and engineering that are involved in building a spacecraft like this?
Yes, I'll go through that. We have multiple subsystems, and each subsystem is really a discipline that we do. So I'll kind of mention the subsystems real quick. There's, of course, the mechanical subsystem, which developed all the structure. There's a guidance, navigation, and control subsystem, which I mentioned provides all of the hardware for controlling the spacecraft and supporting all the activities to point the spacecraft to gather science data and all that. Guidance, navigation, and control works really closely with our flight software team, who generates all the software and the algorithms for controlling the spacecraft, as well as all the data communications and interface between everything. Of course, there's an electrical power system, which for us is the solar arrays and the battery, so electrical engineers, very important for that. We have the communication system, which is a RF S-band system. That's data systems guys, communications engineers, telecommunications and that. We have the CNDH system, so that's a lot of computer science and also data engineers also supporting that activity, so there is some cross-mixing on that. There's the thermal engineers, which I really didn't discuss much on this, but is a very critical aspect of every spacecraft because ours is a passive thermal system. We mainly just have heaters to keep things warm during transit, but thermal is a very challenging item for LADEE because of the long duration and the phasing loop, but also going around the moon, going from sun to dark, extreme temperature difference. So thermal was a very high consideration for us and look at that. So the thermal engineers, and let's see, and of course the propulsion system. So you have the propulsion as a subsystem. So you have fluid systems engineers, sometimes mechanical engineers, and a variety of people for that. And does that cover most?
Yes, thank you.
To add on that just real quickly is we try to transition a lot of those engineers to support the mission operations phase. So we have an engineering support team that supports the mission operations team, which is preparing for launch tomorrow.
You're talking about the spacecraft bus architecture with the stacked modular approach. What's the rationale for the tapered but the tapered edge at the top of the stack? And the second question is, do you know why it's only a 100-day science mission?
Why it's only 180? Okay, I'll talk about the tapered first. The taper comes from a heritage prototype. LADEE kind of started as a lander concept, and a lander, especially on the moon, what you want to make sure you're getting solar energy hitting the top of the spacecraft, those solar cells, it was tapered. For LADEE, they did a trade study and kind of looked at, do we take that taper out or leave it? And the decision was to leave it on, I think partly because there's an angle to the sun depending on when you launch called the beta angle. And if that beta angle is positive, essentially the spacecraft looks tilted relative to the sun. This gives us a little bit additional power for those cases. So they decide in their trade study to keep that. The other question, the duration of the mission, 180 days, that was more of a directed kind of activity that we wanted a short duration mission. There was a minimum number of days that we wanted based on lunar cycle to meet science requirements. So it's really based on that, but it's also based on kind of our fuel capacity. We're weight limited on the Minotaur 5, so we had to limit how much fuel that we can, and the size of the tanks and the fuel that we can put in, and that drives kind of how long our mission is, especially for the big burns to get us out to the moon. So it's kind of a combination. It was decided early on, but it's also kind of a limited life item or a fuel constraint that we have.
That's about all the time that we have for questions here today with Bob here. So thank you all very much. Thank you, Bob, for talking a little bit about the engineering behind this. So now that you guys have heard a little bit about the science behind the spacecraft, a little bit about the engineering behind the spacecraft and everything, now we're going to talk a little bit about getting it ready to go to space. And so up next, we're going to hear from Sarah Daugherty, and she is the test director for the Wallops launch range here. So without any further ado, Sarah.
Thank you, Jason. So as he alluded to, we're all very excited about going to the moon and focused on that, but I'm going to reorient us a little bit back down to Earth just before we launch a rocket to get there. So my position here at NASA's Wallops Flight Facility Launch Range is Test Director. For rocket launches, you can think of that as sort of the launch director. We call it Test Director because there are numerous other missions that we do here, and so the same position and authority resides over those missions there, so we just use the word test to kind of bucket collect everything that we could be the director of all of the test missions that we do. But back to LADEE, so the launch range goes through a lot of preparations in order to support our customer, if you want to think about it like that, which is the LADEE spacecraft that we will have launching from our launch pads here. And so we provide a lot of services to the mission for launch operations. So we provide radar tracking to track where the vehicle is in flight. We provide telemetry antennas to receive data back from the launch vehicle and the spacecraft during flight. We provide command uplink capabilities, and that's also for range safety purposes in case the vehicle does start going off track. We can send commands to destruct the vehicle if that so happens, to keep the public safe, and we've defined hazard areas and things like that ahead of time to account for all of those. So there are numerous things, and maybe you guys, I don't know if you've seen out here some of the telemetry dishes and radar dishes as you came in today. Those will be some of the same ones that we will use tomorrow night for launch to track the launch vehicle as it's going into space. In the control center is the range control center is where all of those services that we're providing will sort of come together. And there are different teams in the control center that are responsible for each of those areas. And then my job is to sort of oversee that as sort of the orchestra conductor and be sure that everyone is going through their checklists and they're doing all the items in the countdown. And once all of the items are checked off and we've worked through any issues that may have come up, to give the final go for launch, or say that it is okay, and be sure the team is very comfortable with that. Like I alluded to before, the radar telemetry dishes, we also have an entire range safety team that is keeping track of preparations on the ground at the launch pad as we're counting down and getting closer and closer to launch for all the site preparations that are going on out there. That team is also focused on safety during flight, so we have a flight safety officer that is monitoring the vehicle flight during launch. And another big part of our launch operation is surveillance. We have to make sure that the ocean space and airspace out off the coast is clear so that we can launch the vehicle out safely and keep the public safe. So we have a host of aircraft and boats that are on our team that are out there working to clear the hazard areas. We work in conjunction with the local mariners here to help us do that. We work with the Coast Guard and the Marine Police and a number of other entities to kind of keep the waterways clear so that we can get a safe, successful launch. So that'll be a big part of our operation that the launch range is focused on during the countdown, while the engineers and the spacecraft team are making sure that their vehicle is okay and going through their checkouts. We'll simultaneously be doing all of those activities. So with that, I think I'll open it up to any questions anyone might have about the launch range or any kind of services or instrumentation we're providing.
Hi, good morning. I'm curious, as you're preparing for launches, why is it important to keep the vehicles and the materials sterile, and what circumstances would the sterility not matter?
That's a good question. Largely has to do, from our standpoint, from the launch range, is the hazards that might be on the vehicle that pose to the folks that need to be working on or around them. And so it's not so much for us keeping it sterile as much as just keeping other things from affecting it, or from the vehicle hazardous systems affecting those folks that are on the ground and on the pad, preparing the vehicle, hooking up the umbilicals to it, and that sort of thing.
Yeah, I live here on Chincoteague and know some of the problems with the marine keeping the area clear. How far south and north are they blocking the area off for this launch?
It's a pretty large hazard area this time, just because the vehicle is so large, a Minotaur 5, and it will be, again, mission of first, the first flight of that vehicle from here. So it doesn't have a history of safe flight. It still needs to build that up. So the area north to south is probably about 20 or 25 nautical miles wide. The largest distance is how far it extends out into the Atlantic Ocean from the coast. That's a pretty large distance, I think a little over 100 nautical miles. So a lot of space there.
Good morning. So does the launch vehicle launch it straight into a TLI, or where does the launch vehicle leave the spacecraft?
The launch vehicle will leave the spacecraft at the orbit insertion point. So it'll be after fifth stage separates from it, and there'll be what we call the orbit insertion point there. And then the spacecraft operations will take over from there and use the propellant on board to push it to the orbit that it needs to go to. That's roughly about 30 minutes after launch. So it takes about that long to get to that orbit insertion point, and then from there it will be solely the spacecraft powering itself and moving on to out of Earth's orbit and to the moon.
Hi. How far in advance do you guys start doing checkups on the rocket, and how's it looking for tomorrow's launch?
That's a great question. The team is usually starts working on the range. We start working several months ahead of time, but right around the 3-week before launch mark is when we're really rigorously testing our systems. We're getting the radars and the telemetry dishes into the configuration specific for LADEE. We are running through practice countdowns, and we're doing what we call dress rehearsals, which is just basically a simulation of what launch day would actually look like. And we run through the entire countdown and make sure all the steps are correct and the right people are making the call outs and all the wording is right, and we have them in the right order. Sometimes it definitely matters what order you do things in. So that starts about 3 weeks out from launch, and then as we get closer into launch, the pace picks up. So this week we had our large mission dress rehearsal on Tuesday, so that was sort of the final practice of the whole team together, and everybody going through the countdown exactly as it's written and planned to be sure that one final check. The range systems are go and ready for launch, so we'll do just a final verification today before launch tomorrow. But right now we're go, all systems are green, and we're ready to launch.
Hello. I was curious, what procedures are you undertaking to reduce carbon footprint for these launches?
Ooh, that's a good question. I don't know that I can answer that. I can tell you that we have here on the launch range, we have an environmental office filled with biologists, chemists, environmental engineers that are constantly reviewing missions and projects that we're bringing here, like LADEE. They do the same for Antares or for a sounding rocket program that we have come here to launch. And so they're always looking at our impact by doing those missions on the environment and how that fits in with overall having sort of a symbiotic relationship with our marshlands and wetlands here. That's sort of the main thing that we're concerned about, just because there are a lot of species and things like that we like to monitor and be sure that we're not impacting them.
This is more of like an environmental question. I'm just wondering, because I know that there's so many laws and things that govern the impact on a marshland or a coastal environment.
Mm-hmm.
And you think of that environment as being in flux all the time. So how in flux is this one, and how are you stabilizing it, or do you not have to, or is it stable?
Yeah, you are correct in that it's always sort of changing. You can see that sort of yearly. The launch island, or Wallops Island, where the actual launch pads are, each year, beach erosion and that sort of thing. That's a very prevalent thing, and so we have project initiatives to kind of firm up the beach with big rock walls and using geotubes and planting beach grass and that kind of stuff to hold the sand in place. So that's just one of several efforts that our environmental office goes through. So I think you hit it right where it is in flux, and there are all those kinds of considerations to take in.
Hi. What are the weather constraints for this launch, and how do the weather constraints for Minotaur 5 differ from other systems?
That's a good question. So there are a lot of weather constraints. I couldn't begin to list them all here. Of course, lightning and thunderstorms, that's a very prevalent one. So we don't want those, anywhere, the potential for lightning, or lightning actually within a certain number of miles of the launch pad. I believe it's 20 or 25 miles of the launch pad. So there's those kinds of constraints. Wind, of course, is always a factor. And ground level winds, as well as upper level winds as the vehicle is progressing up on its vertical flight into the atmosphere. Tomorrow is looking wonderful for a launch. It is amazing at the forecast that our launch weather officer has for tomorrow. Here, being on the coast, we're usually in a weird spot where we're getting some strong sea winds, or the humidity is too high, or there's fog in the morning, or clouds rolling in at night. But tomorrow night is looking very great. I know our launch weather officer actually had a hard time kind of picking something that might come to get us. So he said maybe some low-level clouds. He threw that up as a 5% chance. So that means 95% chance of favorable launch conditions tomorrow as far as weather. So you're welcome.
I had a second grade student when I was saying that the launch was like 11:27 p.m. They were like, well, why 11:27? Why not 11:30? And why at night?
I don't know if you can repeat
that. Sorry. I had a second grade student ask the question when I was telling them that the launch was going to be 11:27 p.m. and to watch it if they could stay up that late. And they were like, why 11:27? Why not 11:30? And why at night? So
yeah,
you're wondering.
I don't know that the day and night doesn't make a whole bit of difference, but it is that exact time. It's best for the most effective time or window from that time plus 4 minutes to get to the orbit insertion point and get onto the moon with the least amount of effort or stress on the spacecraft and those systems. So there's a lot of flight dynamics and orbit mechanics that goes into figuring out that time. That's right, angles and just variability in a number of different things, and that specific time is the best one to hit our target of the moon. All right, is that all? Thank you, Jason.
Thank you. Thank you very much. So our last speaker today is going to actually talk a little bit of something totally different. We're going to change gears here a little bit. This is ways to get involved with this mission. So this is for everyone at home. This is for everyone that's here. This is all sorts of ways for everybody to get involved in this. And so without any further ado, I have Brian Day, and he is the Education and Public Outreach Lead for the LADEE mission from NASA Ames.
Thank you very much. So, as you have heard, LADEE is a very exciting, very interesting mission. But this isn't something we're wanting people to just watch us do. This is something that students and the general public can directly participate in. And we're inviting you all to do that. So next slide, please. Let's go one more time. One more slide, please. So one of the things that's going to happen, and we're waiting for the slide to come up, I'll talk. One of the things that's going to happen is that there's going to be an opportunity for students in classrooms across the country and around the world to directly participate in the science of the mission and even in the operation of the mission. Through a program called GAVRT, the Goldstone Apple Valley Radio Telescope Program, students will be able to take remote control from their classrooms of some of the giant 34-meter dishes at NASA's Goldstone Deep Space Network tracking facility. Using these dishes, they will be able to track and monitor the health and status of our spacecraft in flight. They'll actually be able to do Doppler studies of the carrier coming from our spacecraft. And once the spacecraft is in lunar orbit, they will be able to do basic exercises in orbital dynamics. But the exciting thing is during the phasing loops, they may be listening at times that we are not. So if the spacecraft were to go into safe mode, it may well be a student that hears it first. So this is not looking over the shoulder, this is not role-playing, this is actually participating. Exactly. I'd say next slide, please, but apparently we don't have our slides. Okay, very good. So, in addition, and for me perhaps most excitingly, amateur astronomers. I'm an astronomer myself, and I started out as an amateur astronomer. Amateur astronomers can play a key role in this mission. It turns out that meteoroid impacts striking the moon may be one of the major sources for the lunar atmosphere. And when meteoroids of, maybe walnut size hit the moon, they create a flash that is visible from here on Earth in telescopes 8 to 14 inches diameter. 8 to 14-inch aperture telescope is the optimal range of telescope size to detect these impact flashes. And that's the size of telescope that a lot of schools and a lot of amateur astronomers have. So we're looking to create a network of observers around the world watching for these flashes so that we can correlate these impact events with changes that our instruments see in the structure and composition of the lunar atmosphere. This will give us a better understanding of how these impacts play a role as a source for the lunar atmosphere. Now that's great if you happen to have an 8 to 14-inch telescope. Hands, how many? A few, and this is not a typical audience, I would venture a guess. Most people out there do not have access to such telescopes. That's okay. You can still participate because it turns out that the majority of impactors hitting the moon are actually very, very small. If you do a plot of frequency of impact versus diameter of impactor, it peaks at about 1 micron. Now, a 1 micron impactor is not going to generate a flash that you would ever be able to see from here on Earth. But it turns out that even a very, very small piece of debris, when it hits our atmosphere, becomes very evident in the form of a meteor. When you look up in the sky and you see a meteor, the typical solid object causing that streak of light in the sky is about the size of a grain of sand. Now, because the Earth and Moon are traveling together through space, they encounter these streams of debris together. And so if you were to go out in the night sky and simply count meteors and see how that varies from night to night, we can therefore make inferences as to what's happening on the surface of the moon. The great thing about doing meteor counting is the equipment requirements are absolutely negligible. You do not need a telescope. You do not need binoculars. I do recommend a reclining lawn chair. You might as well be comfortable. But as is the case with almost everything these days, there's even an app for that. Our good friends at the NASA Meteoroid Environment Office have come up with an app, both for iPhone and for Android, ingeniously named Meteor Counter. And the great thing, your phone knows what time it is, it knows where you are. You go out under the nighttime sky and you start tapping when you see a meteor. You tap on the right side for a bright meteor, on the left side for a dim meteor, in between for an in-between meteor. It records all that information along with where you are and what time it is. And at the end of your observing session, it uploads that to NASA. Anyone can be a part of the science of this mission. Now, I'd just like to wrap up that there is more information about Gavert out here in the exhibits area. I encourage you to talk to them. There's more information on the Meteoroid Impact Observation Campaign, the exhibit area for the NASA Meteoroid Environment Office. And if you come by the LADEE exhibit, we have information on Meteor Counter. But I invite you and the rest of the public to join us in this mission and the exploration of the lunar atmosphere. Thank you very much. Sure.
Hi, Brian. I know the Ames Research Center is currently doing some archival work with the Surveyor tapes.
With the Lunar Orbiter
Lunar
tapes.
Orbiter, sorry, yes. Is that information being held by Ames at all important for the fact that Ames is creating LADEE?
Well, it has been very instrumental. So let's talk about some of the things that have been happening at Ames with regard to lunar research. Obviously, we have the LADEE mission. Before that, we had the LCROSS mission that discovered water ice on the moon. And I see a few familiar LCROSS faces out here in the audience, and that makes me feel very good. NASA Ames was also the location for the NASA Lunar Science Institute that was set up and has recently morphed into SSERVI, the Solar System Exploration Research Virtual Institute. Long name. But the impetus behind that name is our turf got expanded. So it's not just the moon anymore. We're still doing the moon, but now we've also got near-Earth asteroids as well as Phobos and Deimos. So we had to expand our name for our expanded playing field. But there's been a lot of research going on with regards to the moon. And the LOIRP, the Lunar Orbiter Image Recovery Project, is something that's going on there at the NASA Research Park there in the Ames area. And that's, so there's been great synergy between this. And then we're working very closely, we've been working very closely with the Lunar Quest Program Office at Marshall, with our friends at JPL, especially the Lunar Mapping and Modeling Portal. Oh, and both of those fine organizations have exhibits out here too. So lots of information for you.
I have a question about the meteors that are impacting the moon.
Mm-hmm.
I've heard that some that they believe there may be water on the moon, and that some of it may be cometary in nature. And what kind of meteors do hit the moon? Are they all just stony meteors, or are they made of other materials?
So what types of meteoroid impacts do we see on the moon? Quite frankly, the majority of the impacts we see are shower-related. So they are related to meteor showers. So a particularly good time to go out and look for meteoroid impacts on the moon is during a meteor shower. Now, I do not want to discourage you from looking on other nights, because even on nights when we don't have showers, there are important impacts to catch. But when we look at these meteor showers, the vast majority of meteor showers are derived from comets. They are debris left behind by comets. And comets are particularly rich in volatiles, including water. So, yes, we would expect to see water as a component in those impacts.
Alrighty then.
Thank you very much.
Thank you very much, Brian. For our audience that's watching on NASA television at home, we're going to go ahead and be leaving you all now. We really do appreciate you all tuning in and watching our broadcast today. If you are looking for how to find this mission, you can find us online on social media. We're going to be doing live launch coverage and mission updates tomorrow night on @NASA and @NASA LADEE on Twitter. Also the NASA Facebook page and the NASA Google Plus page. Moving on beyond there, you can find out more information about this mission at www.nasa.gov/LADEE. That's LADEE. And as always, we're going to do live television coverage starting around 9 p.m. tomorrow night on NASA television. If you want to find out more about that, you can go onto the LADEE website at nasa.gov/LADEE and tune in to watch our live broadcast. And we should have a beautiful night launch tomorrow night at 11:27 p.m. Eastern Time. So look forward to that and you all joining us on there. So thank you very much, and go LADEE.